just a great pleasure to have Alessandra Flammini with us today. As you can see from the title of her talk, she is an expert in distributed measurement and Internet of Things. So she is a physicist. She's a professor at the University of Brescia, Italy, and she has been really pioneering connectivity and, in fact, smart cities, smart living in her work for the past years. I will not take more time in introducing her. You will have a biography on the website to read even more on her absolutely fantastic and stellar career so far. And I will just leave her the floor because I know that she will also mention part of some of her career and her life during her presentation. So with no further ado, I think Alessandra Flammini, distributed measurement and Internet of Things. And of course, Alessandra, it is a great honor and thank you so much for accepting to be one of our extraordinary speakers. And thanks of course to all the attendees. Alessandra.
Thanks to you for everything. Thanks for presentation, of course. And this is the agenda of my talk. As first, just 2 words about my life choices and how I came to deal with distributed measurement and IoT. Then we will introduce the measurement fundamentals, the distributed measurements, and now from smart sensors, now we talk about Internet of Things. After a brief look to the IoT technologies, we will examine some application cases of IoT, showing the most challenges elements. When I was young, after high school graduation, I had to choose the degree course. But it would have been a life choice because on one side, a good marriage, some children, a quite light job that can be combined with family and housekeeping. On the other side, a challenging career in industry or academia. I've never been good with decisions, so I said, yes, I want both. And my mother said, you'll do both bad because there is not time enough. I have had a very lucky life because I met extraordinary people in my life, very good university teachers encouraging me and helping me to find my way, an extraordinary husband who is also my best friend. I found an industry that made me career by showing to the world how progressive it was. Nowadays, my research group is made up of young and great scientists who are also great people. And working together with very good persons is more nice and funny. I immediately gave up on becoming the perfect woman, both in family and at work. And in this way, I also find time for my hobbies. My degree in physics brought me very close to the world of measurement because physics includes the measurement of physical quantities and a lot of experimental setups. After the laureate degree, I joined an industry involved in motor drives, and motor drives means measuring currents, voltages, and other quantities from sensors, and acting with very low latency. Latency is the time between the measurement and the action, and it should be known and well below 1 millisecond and constant. So when 10 years later I joined the University of Brescia, it was natural to me to join the research group dealing with sensors and measurements. In my studies and first job experiences, the keywords were laboratories as first, measurements, and sensors. I joined IEEE 24 years ago, the Instrumentation and Measurement Society, my society, is not the biggest or the most famous scientific community. It is quite small, but with a big attention to youth, and for this I love it. I've been a member of the IMS Administrative Committee in 2013-2016 and by President's Conferences in 2014-2015. I've been in the steering committee of many conferences. I served as technical or general chair of several conferences. It was a nice job as I felt to belong to a group of good friends with a common passion, measurements. Measurements, according to Britannica, is the process of associating numbers with physical quantities and phenomena. Measurement may be made by unaided human senses, in which cases they are often called estimators, or more commonly by the use of instruments. Numbers. Which kind of numbers? As first, the value of the physical quantity and of its measurement unit. But in many applications, it is important to know the time instant related to that measurement. In addition, many other information can be very useful. That is, how the measurement procedure has been performed, which instruments and tools have been used, in which place, and so on. Even if you use the best instruments and if you follow the best measurement procedures, no measurement is exact. When a quantity is measured, the outcome depends on the measuring system, the measurement procedure, the skill of the operator, the environment, and other effects. For this reason, we associate an uncertainty to each measurement. And there is the GAM, the Guide for the Expression of Uncertainty in Measurement, helping us in quantify the uncertainty. The GAM approach is to express the result of a measurement as the best estimate of the measurand, along with an associated measurement uncertainty. Uncertainty evaluation exploits a probabilistic approach, and in this figure, the real measurement is not the red point, but is within the red rectangular due to uncertainty. Measurement requires instruments, and instruments are normally costly, but programmable, with storing and computing capability, and mainly human-oriented. I take the instruments, make the measurement, store the readout, and take the instrument away. But if I want a permanent measurement process, I need cheaper items to live permanently in place. They are the sensors. And the sensor will be connected to a machine as a controller in order to have a continuous measurement process. Normally, sensors encode the information in an output signal, significant in voltage, current, or frequency, or other, in order to be easily acquired by the controller. A traditional distributed measurement system is normally a multi-channel instrument. Each channel has a probe, called S in the figure, through which it is possible to connect the signal or the sensor output to the central core of the instrument. This star topology requires long and shielded wires in order to transport signals from the measuring point to the core, neglecting the electromagnetic noise effect. This architecture is normally used when a simultaneous sampling is needed, and a time-different compensation should be provided when different sensors are used, while cable delays are normally neglected.
Sorry, Alessandra. Someone is not muted from the audience. Would you be so kind of... Tambara, would you be so kind to mute? Tambara?
I think you can mute him.
I cannot. I tried.
Dioredna can mute him.
Yes, Dioredna can mute.
Yeah, I kind of.
I'm trying to. Sorry, I'm trying to
No problem.
for the audio.
I'm not sure who's speaking.
Stationary
Sara Bonifacio.
ibintu ni printing z'ibintu wakoze ibitabo iki.
Okay.
We need to have receipts.
I can.
Sorry, Alessandra, go ahead.
No problem. Okay. The central core of the instrument we see before can be greatly simplified if the distribution is about information instead of signals. A normal computer, a PC, can be connected by a real-time communication network to many so-called smart sensors. A smart sensor is a sensor with communication capability providing pre-processed information. This architecture has several advantages with respect to the traditional one, as it requires shorter wires and a simple controller, but it requires real-time communication network to ensure a common sense of time among all the distributed measurement. Smart sensors are sensors with communication capabilities, providing information ready to be used and providing diagnostics. They are a little bit more complex and costly with respect to the traditional sensors. In this slide, we have 4 types of sensors, just to make some example. From the right to the left, the first one is a traditional sensor, and the main advantage is cost, and that the controller can have information with the shortest latency. The second one transmits on a digital network, but the information is not ready to be used. What does it mean? 2715. I need the temperature. And so a lot of a priori knowledge is required. In this case, the digital network is probably a simple serial link introducing a constant delay on the order of 1 millisecond. The third one is a true smart sensor, a wireless smart sensor, providing information ready to be used, the temperature in Celsius degree, and diagnostics. Latency is a little bit worse with respect to the previous case, on the order of tens of milliseconds, because of the unreliability of the transmission medium, that is the air. The fourth one is connected in cloud, and information are available by application programming interface. In this case, latency is on the order of hundreds of milliseconds. There is an IEEE standards about smart sensors, the IEEE 1451. According to IEEE 1451, a smart transducer is a transducer that provides functions beyond those necessary for generating a correct representation of a sensed or controlled quantity. This functionality typically simplifies the integration of the transducer into applications in a networked environment. An IEEE 1451 smart transducer can identify and describe itself as processing capability to present sensor data or actuation values in measurement units, as network access capability, is easy to use, and it enables plug and play. Plug and play means that if I replace a temperature sensor by a manufacturer with another temperature sensor by a different manufacturer, I do not need to change the software, but it's the sensor itself that provides all the information needed to retrieve the measurement. This slide highlights how the final destination is Internet, regardless the network technology and topology. At the top, there are the applications, requiring measurement information and providing data and commands for actuators. The green circles are sensors, and from the left to right, we have different topologies. We can have a single sensor, we can have a star wired network, an infrastructured wireless network like in Wi-Fi, a star wireless network as in Bluetooth, a mesh wireless network as in ZigBee, and other technologies. In any case, there is a common and known interface provided by the standard, the light blue circles, the network-capable application processor information model, the standardized interface toward applications. Let's go to applications and focus on performance and real-time behavior of a distributed measurement system. We suppose to have an Ethernet network as it occurs in industrial application. Switches receive a packet and forward it to the recipient on the correct path. Switches have memory buffers to store messages if the path is temporarily occupied by other traffic. But this mechanism introduces unpredictable and variable delays. So the need is the characterization of the network delay. A distributed instrument to characterize the Ethernet network delay is not a trivial tool. The probes of the instrument should be very finely synchronized, well below 1 microseconds, to share a common sense of time and finally timestamp the time instant of the passage of a certain packet. In this measurement set up about 15 years ago, the main problem was probe synchronization, and we use another IEEE standard, IEEE 1588, the so-called Precision Time Protocol, that nowadays is supported by Industrial Switch for Real-Time Ethernet. In fact, every probe has its own clock, but clocks can go faster or slower, and NTP, the network time protocol normally used in Internet, allows uncertainty on the order of 1 millisecond, that is too big. So, why PTP is better than NTP? How these protocols work? The basic mechanism is the same, and it is based on the valuation of the round-trip time. We have a master clock with a correct clock and a slave clock, whose clock needs to be adjusted by a term we call offset, off, in the equations. The time TS1, in which the slave received the sync message sent by the master in TM1, can be expressed as the sum of TM1 off and the master to slave delay of the message sync. The message delay request sent by the slave in TS2 is received by the master in TM2, and if we suppose a symmetrical delay, that is, master to slave delay is equal to slave to master delay, it is easy for the slave to compute the offset starting from TS1, TS2, TM1, TM2. Normally, the sync message, that is multicast, one master clock to many slave clocks, is much more frequent than delay request message. Therefore, off is updated more frequently than the delay between master and slave. Uncertainty of the method depends on uncertainty of the timestamping mechanism, and PTP has hardware timestamping. It depends also on the time interval between two successive sync messages, and if the architecture has more than 2 nodes, it depends also on the propagation method of synchronization, on the master selection, and so on. So PTP is much better than NTP because support hardware timestamping and the knowledge of TS1, TM1, TS2, and TM2 is much more accurate. The sync message allows the slave to calculate the offset and to subtract it to its own clock. Keep in memory of the offset behavior, the slave can also estimate the slope that indicates if its own clock is slower or faster than the master clock. Starting from the slope and offset, the slave can dynamically adjust its own clock, providing a much more accurate software clock. But there are really applications requiring synchronization below 1 millisecond, requiring PTP instead of NTP? Oh, for sure, in subatomic particle accelerators. But also in motion application, where motors must be coupled by current, and in smart grids. In fact, if we have measurement only, a fine synchronization is really very important for the science to better understand phenomena and to improve diagnostic, cybersecurity. But if the measurement is devoted to perform the right action with very low latency and jitter, that is, in the real-time control systems, synchronization is mandatory. In the substations for electrical energy transformation and dispatching, the real-time control is performed over a communication network that is regulated by the standard IEEE 61850. The process bus, the more critical concerning synchronization, includes two forms of communication: GOOS, generic object-oriented substation events, and SMV, sampled measured values, both requiring real-time behavior. Particularly, the interval time between samples is 250 microseconds according to the standard, very small, and it is defined a special IEEE profile of PTP in power system application. This very good synchronization is mandatory for action on breakers, but it is also very useful at the station level and at the so-called cloud level for diagnostics in order to evaluate phenomena and realize a sort of digital twin of the substation. Generally speaking, when we talk about distributed measurement, we have three levels, as we have seen for the standard for smart sensors. And this is the slide we have seen. The sensing level, including the physical principles used by the measurement of a certain quantity, the networking level, and the application level. If the network is Internet, we talk about the Internet of Things. We have a lot of definition for the Internet of Things, but I like the one of the IEEE 2413 standard for an architectural framework for the Internet of Things. Internet of Things is a network that connects uniquely identifiable things to the Internet. I like it because it is short and it emphasizes that things are uniquely identifiable with an ID, a place, a time, a quality, and so on. The boundary between the concept of Internet of Things and of cyber-physical systems is very light. Cyber-physical systems, according to the National Institute of Standards and Technology, are smart systems that include engineered interacting networks of physical and computational components. So, IoT emphasizes the unique identification, the connection with the Internet, and the accessibility of real things, while CPS emphasizes the interaction between real physical things and virtual cyber things. We can say that under a certain point of view, CPS use and extend the IoT to the cyber level. Often, IoT and CPS concepts are linked to the digital twin concept. Put simply, a digital twin is somewhat the result of a learning process applied to a cyber physical system. Coming back to Internet of Things, the application level is normally realized as cloud computing. Cloud computing in IoT is used to store IoT data and provide services. The remote computing increases the latency, and in those applications requiring a short time elapsed from the event to the related action as industrial application, fog computing is preferred. Fog computing is a sort of extension of cloud computing to be closer to the things, achieving reaction time on the order of milliseconds. The fog is connected to the things in real time, while it is connected to the cloud in a more relaxed way. Edge computing is a kind of extreme fog computing. Edge computing is about placing computational resources as close as possible to the source of the data and where the action needs to be taken. We have on the left devices tailored for Internet of Things. We have ultra-low power microcontrollers, programmable in C, no operating system, no update firmware. If you want to change the program, you must flash the device. On the right, we have edge computing devices, 16/4-bit, Linux-based, fully programmable microcomputers. Thanks to edge computing architecture, you need less communication, and you can achieve a short delay from sensing to action. Common communication technologies as Bluetooth, Wi-Fi, 4G have been designed for big and complex data as files, audio-video streaming, and so on. Throughput, that is the mean amount of transferred byte per second, is the key point. Communication for sensing manages typically very simple data as value, timestamping, diagnostic information. So the key points are latency, jitter, power, range. It depends on the chosen application field. In addition to operational technologies as field buses as Profibus, Modbus, Wireless ART, and other, recent communication technologies for IoT can be divided in two main blocks. On one hand, we have the real-time Ethernets that are wired, low-latency technologies, and you can see some commercial solution on the left. On the other hand, the wireless solution where low power and wide range are the most important key points. The battery should last for years, and the range should be hundreds of meters. And you see some commercial solution. The two different blocks of IoT technologies correspond to two different blocks of applications: massive IoT and critical IoT. Massive IoT concerns many very simple, low-cost, battery-powered devices with very relaxed time constraints. On the contrary, critical IoT concerns reliability, availability, and low latency. Let's focus on massive IoT. Also because technologies are growing and improving fast, and what is critical today can be easily available tomorrow. The communication technologies expressly designed for massive IoT are called Low Power Wide Range Networks, LPWAN. The coverage is on the order of kilometers, battery life is on the order of years, device cost on the order of few dollars, and the network should be very easy and inexpensive to deploy and manage. Here is a not exhaustive overview of many technologies and commercial solutions. We can have technologies operating in the licensed spectrum, that is, you pay a provider to communicate, and technology in the unlicensed spectrum. Adopting a technology in the unlicensed spectrum does not mean that you for sure do not pay, because if the solution has a public infrastructure, you pay the infrastructure owner, but costs are very low, and to realize a private infrastructure is very easy. On the right, you can see some applications, some solutions that are not exactly LPWAN, but they can be used in massive IoT applications. Here you can see a brief comparison among main technical characteristics of some solution. The choice is not simple as in many cases it occurs. In my case, the choice was really very simple because my town, Brescia, has a public LoRaWAN infrastructure provided by the multi-utility, that is the distribution system operator, and the municipality server provider. What is LoRaWAN? LoRaWAN is long-range wide area network, and it adopts a star-of-star topology similar to mobile networks. The gateway is the center of the end device star, while the network server is the center of the gateway star. It is very simple to realize a LoRaWAN end device, and you can find in the Arduino community, for instance, and it is easy and quite inexpensive to realize a private LoRaWAN infrastructure. The backend of a LPWAN takes care of the network management procedures, and in LoRaWAN we have a network server taking care of frame exchange, an application server taking care of data, and a joint server taking care of authentication of communication between an endpoint and a server. The user application has a simple interface to the LoRaWAN backend. Okay, we have seen many pros. Is there some cons? I'm not a LoRaWAN seller. LoRaWAN has three communication classes, A, B, C. We consider A class that is the most popular thanks to the very low power. The node, in order to save power, and it is not so easy to have a battery life of 10 years, periodically wake up, send a message we call uplink, waits for 1 second, listen for messages, downlink, waits for 1 second, listen for message, and goes back sleeping. The industrial, scientific, and medical band, that in Europe is 868 MHz, has power and duty cycle limits. The node has a limit in transmission duty cycle equal to 1% in 1 hour. This means that if the node transmits for 100 milliseconds in air, it has to wait for about 10 seconds before transmitting again. The duty cycle limit is applied also to the gateway, who transmit in downlink to many end devices. So a typical application has end devices transmitting every minute and receiving every 20 minutes or more. Internet of Things has really a lot of applications because people communicate a lot, even with things. According to the Ericsson Mobility Report of February 2022, there are 8.2 billion telephone SIM cards worldwide in 2021, and they were 7.8 in 2018. More SIM cards than humans since 2018. But the growth of SIM cards in the last 3 years is nothing with respect to the growth of data traffic. We have 84 exabytes, that is 10 to 18 bytes of monthly data traffic in 2021, and they were only 28 3 years ago. Data traffic is really exploding, and this is one of the main reasons for the new approaches such as fog computing or edge computing that want to limit data traffic. Industrial Internet of Things responds to the need to join operational technology to Internet technologies. Sensor should provide measurement information for control by means of operational technologies and, in the same time, provide data to the cloud according to the Internet of Things. As you can see in the figure, the concept of industrial IoT is quite similar to the definition of cyber-physical system. There is a need to improve performance without increasing cost and without increasing too much data from existing systems, from operational technologies whose main task is and should remain control. What does it mean elevating an industrial plant to the industrial Internet of Things? For sure, adding a lot of software, a lot of information technology systems, and adding new IoT sensors. In addition, turning traditional machinery into smart connected machinery. The retrofitting of a plant or of an equipment is the process of revitalizing it instead of replacing it with a new one. In the traditional plant, the PLC is the aggregating point of data at the field level, that is, the field level is the level of sensor and actuators. The PLC sends a selection of data to the SCADA, and the SCADA transmits them to the ERP system for the management of the whole plant. This data flow is for the operating, and it is not suitable to be used also to emulate a new IoT-enabled industrial architecture, where sensor, actuators, and peripherals are real IoT devices and send information to the PLC for control and to the clouds for analytics, management methods, and predictive maintenance. PLC and SCADA cannot be used as gateway, rewriting their software, as well as all sensors cannot be replaced with IoT devices because of the cost. So the idea is to retrofit a legacy PLC with the LoRaWAN. This is the experimental setup to evaluate the retrofitting of a possible machinery controlled by a PLC. We add to the PLC a serial module connected to a LoRaWAN module, and we have developed the software to transmit an uplink message of 18 data bytes every 63 seconds. In this way, the existing software of the PLC remains, ensuring correctness of the operational behavior. The end device is a Siemens IoT 2014 and MQTT broker has been used to access data. A downlink message is sent by the IoT 2040 every 20 minutes. Timestamping of the message is ensured by an NTP server. Uplink data are generated by the PLC at T1, timestamping by the application server at T2, and received by the endpoint at T3. Downlink data are generated by the endpoint at T4 and received by the PLC at T5. Unfortunately, the MQTT broker cannot timestamp downlink message. A public LoRaWAN infrastructure has been used, and traffic has been observed in order to test performance in two different traffic scenarios. It should be noted that the overall PLC to endpoint delay, P2E, is heavily affected by the traffic. On the contrary, downlink overall delay is very big, as it depends on the time period between two successive uplink, that is 1 minute, so the traffic effect is negligible. In conclusion, this retrofitting approach is very minimally invasive because it is not affecting existing software and does not require new cable. but it is suitable for monitoring and analytics purpose only, not for control. Just to have an idea of what IoT can do in smart grids, I would like to show you the LUX laboratory in my university that have been realized starting from 2015, and every year I add a piece more. The idea was to add plants and IoT to the engineering campus of Brescia University, making a living laboratory on smart grids and smart living. Oops. This very short movie will take you inside the LUX Living Lab laboratory and inside my university. So in this way, it is possible to remotely control and monitor a campus, a university campus, concerning electricity, power, and living, because we have also a lot of indoor sensors. I've prepared these slides only if there were problems with the movie, so we can go ahead. One of the critical points of IoT-based systems is cybersecurity. In this work, we have emulated a man-in-the-middle attack to the distributed energy storage system. The attached system is the communication over Modbus TCP among smart meter, providing power of the point of common coupling, the battery energy storage system power conditioning system. Battery energy storage system is indicated as BESS, providing BESS power and state of charge of the battery, and the BESS controller, providing BESS power request. The logic is to charge the battery if we have photovoltaic overproduction and discourage grid consumption. You can see the effect of the attach in terms of storage power and the state of charge. The black line is the behavior without the attack, as the medium behavior in past similar conditions. The blue line is the fake behavior, that is the behavior the man in the middle says to the BESS controller. And the red line is the real behavior of the system under attack. And you can see that the system crashes. This slide shows how the electric vehicle supply equipments are mainly IoT devices. You have a non-exhaustive list of communication functions, all cloud-based. there are mainly three domains: the grid, the electrical vehicle with the user, and the interface. The vehicle itself communicates about authorization, charging, smart charging. What is smart charging? Is adapting the charging cycle of electric vehicles to both the conditions of the power system and the needs of vehicle and user. The user communication is more complex, includes billing, registration, reservation, information, while the grid is interested to balance the demand response. The electrical vehicle charging involves many actors who are responsible of different services and functions. However, there is not a unique communication standard taking care of all the possible combination of actors and functions. So, there are a lot of communication standards concerning the electrical vehicle chargings. All new problems with respect to traditional vehicles moved by fuel. And also in this case, cybersecurity is a key point because we have many hopes, many communication gateway interfaces that are all weak points for cyber attack. Communication between the vehicle and the charging point requires real-time data while the vehicle is at the charging point in order to have a smart charging, balancing the power demand response and following the best charging profile for that car and that user. Thanks to this data and to user mobility data, it is possible to elaborate forecasts and surveys helping the distribution system operator. In order to elaborate short-term forecast, communication is required also when the vehicle is moving quite close to the charging point. And in this case, LoRaWAN can act as a backup or a low-cost alternative communication with respect to 4G and 5G. There is not only the communication between the vehicle and the charging point, there is communication between vehicle and the road infrastructure, fundamental in the case of automated vehicles, communication among vehicles, and generally speaking, the so-called vehicle-to-everything communication, the V2X. But two seminars will be held in October, focusing on automotive communications and automated vehicle, and I'm really excited to listen to their talks. So let's go back to the IoT. The concept of Internet of Vehicles arises from the union between the Internet of Things and the so-called intelligent transportation systems. ITS are systems in which information and communication technologies are applied in the field of road transport, including infrastructure, vehicles, and users. The 1 billion of current vehicles are supposed to double within 2035, and many vehicles are already sensorized and connected. That is, there is a communication device that potentially connects all the onboard sensors with the cloud. Internet of Vehicles is a unified framework including intervehicular communication, intra-vehicular communication, and communication between the vehicle and the Internet, allowing services regarding the road infrastructure, such as traffic, lighting, and dynamic information service. As Internet of Vehicles concerns also actions as lighting, traffic light management, speed monitoring, alarm condition alerting, and others, timeline is essential, and for this reason, IOV is in the critical IoT, as well as real-time factory automation and industrial applications. For the retrofitting of existing industrial plants, also for Internet of Vehicles, we have designed and experimentally characterized a solution to enable traditional non-connected vehicles to the cloud. Also, traditional cars have a lot of onboard sensors and microcontrollers. They are accessible by the OBD2 connector, the onboard diagnostic connector. AutoP is a cloud-based framework that, thanks to a connected telematic unit, can export all the onboard sensors value to its remote cloud. The telematic unit is an edge device based on a Raspberry plus a 4G module. The AutoP framework has also a car emulator. We have used the car emulator, highlighted by the red dotted line, composed by a software and a device to connect the AutoP telematic unit, the ATU. As the ATU is based on a Raspberry, it is possible to add LoRaWAN connectivity to the ATU. By this way, we can compare the two Internet of Vehicles solutions. We have measured the endpoint-to-endpoint delay in 4 situations, using the AutoP Cloud and the 4G as the network, using the AutoP Cloud and Wi-Fi as the network, and using the LoRaWAN Cloud under 2 traffic scenarios. Experimental results shows how the AutoP solution is almost independent from the communication technology, and LoRaWAN solution, as we have already seen, is heavily affected by the traffic condition. E-vehicles are connected to support charging, so we will have a lot of connected cars in the next future, increasing a lot the traffic, the data traffic. Multimodal transport, the integrated use of several different forms of transport, is catching on in urban and mixed scenarios. And this growth of electric bikes and scooters is a very good news under many points of view. Pollution, energy saving, healthy lifestyle. Electric light vehicles normally use the user's smartphone for connectivity. But when the user is away, for instance, a GPS for localization could be very useful to remote monitor the vehicle. Normal bikes does not have sensor, neither connectivity. LPWAN, a low-cost battery-powered technology, could be a solution. And I really think that many challenges awaits for Internet of Things enthusiasts. So we will have a lot of job. And I thank you very much for your attention. And of course, I'm available for questions.
Thank you very much, Alessandra. I think there will be, of course, a lot of, let's say, challenges, but we had a lot of inspiration from your talk today. So I have a few questions here from the chat that I'm going to move on to you. And for more questions, please put them on the chat or you can unmute. We have a couple of more minutes for talks, but I will start with the one from Pilar Gomez, Jill. And she is asking you, first of all, thanking you, of course, but she's asking you to summarize what features make a sensor intelligent.
Sorry, I don't see the chat.
So I'm just summarizing that to you, but that at the bottom you should have, if you go with the mouse at the bottom, you should be, you should see on the right an icon. So if you just move the mouse on the top of it, it should really come up and one says chat, and it has an icon which looks like a chatting icon.
Okay.
But anyway, I can summarize them for you if this is okay. And so
Pilar,
yes. Right, Pilar is asking which features are making a sensor intelligent?
Oh, as first, communication, because a lot of things are intelligent because they have a microcontroller inside. Microcontroller cost nowadays is very, very, very little. So almost everything has a microprocessor inside. When we buy some dress, there is inside a microprocessor into the label. And so microprocessor is not enough to make a sensor intelligent, to make a sensor smart. It is needed the communication capability, and particular internet is favored, and the capacity to communicate the quantities ready to be used. So in the example, temperature in Kelvin or Celsius degree, that is a universal way to communicate the temperature, not with a code that is difficult to be read.
Thank you very much. Thank you.
Thank you.
So someone was asking if this absolutely fascinating movie that you showed about the system that you put together actually at your university, so if all the overviews, they were made using a drone.
Yes, we use a drone, and we use also smartphone to realize the movie.
Okay.
But we have an original movie because we have a financed project together with the distribution system operator of Brescia municipalities. And so it was initially realized in 2014. It was conceived by a professional company, and it was realized in 2016, and then we cut some pieces, adding something more every year because we add new equipments. Now we are realizing charging station for electric vehicles that is completely powered by photovoltaic systems.
No, it was really fantastic. And by the way, the question is from Holly Handley. So I don't see more questions from the chat, and I would like to ask you something. So you mentioned 1 millisecond as the current time frame or time resolution for transmission. What would be the next time? So what is really the next in line time transmission resolution that is coming?
Oh, 1 millisecond is the resolution at the internet level.
Right.
But if we think to the local area network as PTP in real-time Ethernets, we are well below 1 microsecond. We have in commercial industrial system, we can achieve synchronization on the order of hundreds of picoseconds.
Oh, wow. Hundreds of picoseconds.
Yes. A component of my research group now is at CERN, is synchronizing all the measurement equipment for particle accelerator.
Right, and so we are getting to the. I guess I know that a lot of big systems, they can get to a synchronization as a system within, let's say, a couple of hundreds picoseconds. But having that long ranges, I think it is really quite remarkable. So fantastic.
There is a technology that is called White Rabbit. I've talked also with a great scientist that is Allan, who is invented Allan variance. is the gotha of synchronization.
Wow, it's so fantastic. Also because at a certain point we will have to deal with all these increasing data. And so we will end we will need really to discuss the challenge of data storage.
Yes, yes. And now we are making a lot of research work on cybersecurity, because we have seen that concerning electric vehicles and smart grids, cyber attacks are the real risk to prevent the evolution of these systems.
Thank you. So I can see that a lot of people have wrote on the chat, thanks for your presentation. And we reached, of course, the hour, so it's probably time to finish. I've been just posting now for everyone who would be interested in looking at the registration or passing through the registration of this presentation. It is on the website. You will also find the past talks. You would also find future talks, and in particular the links and times for the ones that Alessandra very kindly introduced in her presentation. So I think we probably can close that now. I would like to thank you all for attending. Just a reminder that this series, the seminar series, is under the umbrella of the WOE, so the Women in Engineering 25th anniversary. And so Alessandra was representing the Transmission and Measurement Society today, and so we will have representations of many other societies with extraordinary women, just showing the amazing and extraordinary work they are doing. So Alessandra, thank you so much. You've been inspiring all of us, giving a lot of ideas, and I really will be looking forward to continue the conversation, because it is true that there are very, very many things that you are doing which are interdisciplinary, and I hope that you will have you've been inspired as much as I have been, and you might even continue this type of conversations with other applications, other measurements, and Internet of Things. Thank you all. Thank you, Alessandra, again.
I would
and
like to thank
see you all.
all the audience. Thank you so much for attending.
Thank you. Thank you, everyone.